All right, welcome everybody to this live coding session on model development. We're going to see some pretty cool stuff today, so I hope you're excited. Just grab your computer, log into a terminal, and let's get cracking. So for me, as always, I'm going to be working out of my MLOps central repository. If you haven't done so, just go ahead to the Google Drive, check out the comments if you're on YouTube, check out the centralized repository if you're on Udemy. You can grab the material for today's live coding in there. Well, it's basically called class 3, right? So if you grab that, you should be up and running quickly. What we're going to do quickly is we're going to do something like conda and list. We're just going to make sure that we're working in our virtual environment called MLOps. Obviously, whatever environment you've created, just get in there. And we're going to launch a Jupyter notebook where we're going to start the live coding with a bit of code that we see on this notebook. And then we're going to see how we take this code, we refactor it into scripts, and we start scaling things out so that we start doing things that are a bit more interesting than running models in local. So let's get cracking. And with that, we should be able to head to the notebooks, take the class 3 model development. Take this one, don't take the solution yet, just take the class 3 model development. I always make a copy of it so that I don't really change it for me, but make sure that you work with this model development file. And I'm just gonna open this one. And if you remember correctly, we're trying to predict whether we're gonna win a hand or not by training a model to look at the cards that are dealt to us at the game of Ballot Manier. We see these cards, that's a pretty bad game. I have 1 jack, I have only 4 hearts, but they're pretty low. They're actually closest to the lowest one. I have nearly no spade, so I'm gonna run dry of spade very quickly, and he's gonna be able to attack me pretty fast on this spade. And well, the only thing that I can somewhat defend me decently is at clubs. But if I beat at clubs, there is no way that he's going to accept that. If I do a club bid, he's probably going to go up in the bid. He's probably going to go up towards diamonds, where I have very few diamonds, or maybe up to spades. And there's going to be nothing I can do. I won't be able to defend myself. But you know what? I'm just going to try and see if it lets me play at clubs. So I'm going to play at clubs here, and I'm going to see what happens. Well, this is exactly what I feared. This is exactly one of the worst case scenarios. Well, actually, out of the bad things that could have happened, him betting at heart is definitely not the worst, because I have a pretty long suit. I have a 10 that is completely protected. So I have 3 hearts to protect my 10 here. If he decides to attack me quickly at hearts, I will be able to defend me. But afterwards, except the maybe 21 points that I'm going to be able to make at clubs, I'm definitely not going to do any other points than that. So I don't think that I'm going to bet higher than hearts. I'm just going to pass. I'm going to let him take all the risks, and we'll see what he does. I'm pretty sure he's going to go up. I don't think that there's no way he's going to let me play at hearts. Well, obviously, he doesn't know that I have 2 hearts in my hand, right? Just like I don't see his card. He doesn't see my card here. So he doesn't know that I have these 2 hearts that protect my 10. But I would be very, very surprised if he doesn't go up at spade. Maybe he doesn't have the jack or the 9 of spades, so maybe that's why he doesn't go up. Let's see. Our best shot here is to pass and to see if he lets us play at hearts. Yeah, fantastic. Now we can play a game. It's not going to be too bad. So everything we just did right now in the past 2 minutes is exactly what we want to automate with our machine learning model, right? We want our model to do the same thinking as I do, look at how many jacks, how many hearts do I have, and automate this decision-making process, which he's going to be able to do much faster and with, let's say, much more accuracy than I do, right? I have a human brain, so I can process a lot of complexity, and I'm pretty good at the game. I can take good decisions sometimes, but I definitely will do mistakes because I'm a human and I cannot consider every possibilities. And I think that in the long run, our model, if we train it properly, is going to perform much better than we do. So just like I'm able to see all the cards here, we want to find a way to feed these cards as features to our model, and we want to be able to do that so that he understands how to train. And we already spent a bit of time last time on the feature engineering part of things, up to the point where we had a pretty good data set that allowed us to tell our model how many cards he had in each suit, how many cards he had in each card itself, like how many jacks, how many seven, things like this. Whether he had like any points, like blood points or tiers points, like all of this kind of stuff, which is useful information to take a decision. And in fact, as you could see, this is exactly what I was doing myself. I was kind of counting like how many hearts I had so that I could protect my 10. And I was like counting how much point I had initially, like 21 points if I were to play at heart. Like all of this is basically the features that we gave our model. So if we jump back in our notebook and we go back to running, let's say, like the first few cells. Again, just make sure that here you replace this base path with a pointer to wherever you want to store your data folder that you find from the Google Drive inside of your local environment. Just make sure that you point to this data folder and that you point to the files. Today, we're going to be working not with the synthetic data contract, because we've already implemented the first pipeline that goes from synthetic data contract to feature store. So actually today, as a starting point, we are going to be starting from feature store, which we have stored already, if you remember correctly, inside of our BigQuery environment. We have stored this data inside of our BigQuery environment. We can query our feature store anytime we want, so we can get access to this data. We could actually like query it and then download the file and put it in our local repository, or we could implement BigQuery connector, BigQuery Python connector. We could create like a BigQuery Python connector that allows us to run some custom query from inside of our environment. So we would be able to do something like from Google import BigQuery, just set up some kind of client and run some kind of queries here, like get all of the rows from whatever, like our, Bellot feature store, just download everything, and then we would be able to have this data in local, right? So that's definitely something we could do, and you can do that at home if you want to play with the Google BigQuery API. But here, in the interest of time and simplicity, what we're going to do is we're going to jump into this model development module here. We're going to read as a CSV the feature store that we have saved. Not the one, like here we don't do a read from BigQuery with the connector, but we just read it locally from a local CSV that is stored, like my own machine. So that's exactly where I have the pointer towards the CSV in my local repository. Just make sure that you grab this data and put it in your local so that this works out of the box. And once you do that, well, we're going to read like a sample size of 10,000 rows. And then we're going to check the data that we have here. And if you follow the feature engineering module, this should be somewhat familiar to you, right? You have the contract that was played. We keep that for segmentation later. I'm going to talk about this. We have the reward. This is going to be our target variable. Well, actually, this is not going to be exactly our target variable. If you remember correctly, instead of wanting to predict the reward, we're going to want to predict something else. We're going to want to predict whether we have won or lost the game. And this is enough to start with. This is enough, like, turning this problem as a classifier to begin with is a good thing. It's going to simplify quite a bit the modeling. And, at the end of the day, specifically for the game of Ballot Manier, you want to know whether you're going to win or not. You don't really care too much about the amount of points that you do in the end. And that is why exactly we create this categorical variable that tells us whether we've won or not. And so we have, aside from that, a bunch of features from who is the last person to bid, who's the first person to start, how many points do I have when I start the game, how many cards do I have at clubs. This is a very, very interesting feature because you just saw me talk 2 minutes about the fact that I had some pretty good clubs in my hand. I had 4 of them, which is not a lot, but I have like 4 very powerful of them. Like a huge chunk of my decision to actually bid at clubs was actually driven by the fact that I had 4 clubs in my hands. So you can already see why this feature here is such an important feature to feed to the model and how good the decisions are going to be when this feature is put at the forefront of the decision-making process here. And so all in all, what we have is pretty fair data set that should allow us to automate the decision-making process here. That's exactly what we're going to be doing in this module on model development. We're going to come here straight away, and we're going to see if we can train a model to make the decision to play or not play the hand. If I have to contrast what we're going to do today to what we did with the feature engineering last time, here we're actually going to spend a little less time, let's say, on the code. We're going to go pretty fast on the code, and I'm going to assume that a lot of the code that we see today is kind of stuff that you've already seen before, especially if you come from data science or from analytics and this kind of stuff. You probably have run some kind of modeling before. So I don't think there is a lot of value from me, talking too much about this development code. But where we are going to spend a bit of time is in the refactoring of this code and the launch of this code in a scaled up environment, right? That's where I want you guys to get some value today. I will show you how to leverage some pretty good Google Cloud technologies to run everything that we do today at scale. And essentially, I'm going to talk about the labs that we have. Like if you're on Udemy, you're going to have access to all of the labs, so don't worry too much about it. But I am going to walk us through the labs, and we're going to spend a bit more time understanding exactly how the lab is structured and how to run the lab. You're going to be able to do that by yourself at home. But yeah, I want to spend more time on this Google Cloud technology part of things today, so I hope you're excited. So first of all, what we're going to do here is we are going to set our target variable to P1 has 1, right? Because this is what we want to do. We want to predict whether we can win or not the game. We're going to keep these two variables, the reward and the contract, as what I call segments, right? Segments is basically some feature, like some columns that I want to keep for later. Once I have trained the development model, like once I have trained it and I've started to run a few predictions in my testing set to see how well the model is performing, I want to start looking at the errors that the model does, right? And there's nothing more powerful than looking at the errors and seeing whether you start making a lot of errors when, for instance, the game is very tight, have a very tight game where you win at, with only 10 points, or if you make, for instance, a lot of error when the game is very loose, right? You tend to not be able to predict very well if you're going to win or not at 298 points of reward. And intuitively, it should make kind of sense that if we train our model correctly, our model should be very good at telling you that you're going to win the game if the game that you actually win is a game that you win by a lot of points than when you win a game by only a few points. Because these are a very tight game, and it's probably very hard to say whether you win or not, even for a human. And these are a very loose game, where it's very easy to say, like, okay, you have an amazing hand, you have like 100 jacks and all the points at clubs and everything, you should win this hand. So we're going to keep these segments so that we can check later that we have trained our model properly. We're going to keep the covariates or the features as basically, let's say, all of the features that are not the target, right? This is how we're going to define this for now. And we're going to set a base threshold, which is if the predictions of our model are above 0.5, just say that we are going to win this game. And if it's lower than 0.5, just say that we're not going to win this game. So this is a pretty basic and arbitrary threshold that we're going to be using later. And so the first thing that we're going to do is we're going to split our feature store, which contains all of our feature data. Remember, we have our feature data here. If we go to BigQuery and we check what we're working with, well, actually I could do that in local. This is our feature data. We should be able to have enough sample to train our model. Well, actually I read only 10,000 samples just to speed up the whole thing. Afterwards, we're going to see how this runs with more samples. But so now we come here and we kind of like split this training set into a bunch of different sets. So our covariates training, so these are going to be the features that we use to train our model. These are going to be the features that we use to test that our model is performing well. And these are going to be the target variables so that we can train our model, and then the target variables so that we can test whether our model is performing well or not. And so the first thing that I need to do is split this data set. I'm going to use a utility here from sklearn. I'm going to use this train test split here, which is going to be very useful to create those 4 data sets without me having to do too much code. And we're going to make sure that we keep 25% of the samples in the test set. So we're going to be doing that by checking out the API because I completely forgot how this works. Train test split, let's see. Train test split, test side. Okay, that's what we're going to need here. We're going to need this test side and we're going to need to make it, 25%? Can I do that? Can I give it like 25%? Well, actually it seems to be in percentage already. So I should be able to do something like this. And I'm going to pass it the random state so that, we always have the same output that's generated from the development. At least for the development process, it's pretty useful to have that. All right, we start from our initial 10,000 sample rows and we divide it into 7,500, 2,500, and that's pretty good. So now we can safely move on to the preservation of the segments. I'm not going to spend too much time on this because it's not too important for us. The only thing that's important to keep in mind is that now that I'm preserving the segments in our segments covariate training and testing so that I can afterwards learn where our errors are distributed. This is kind of the old econometrician in me that's waking up and that always manifests itself whenever I do some machine learning engineering. I just need to know how my errors are distributed. And so now that we've done that, I can just go to the covariates and not just keep the features that are different from targets, but I can also keep the features that are different from segments. Okay, so now I have all of my covariates here, and these are going to be the covariates that I use to train my model. And so the first thing that we are going to do before anything else is we're going to get a feeling for the bias and the variance that we have in our dataset. As I was saying, like in the theory part of the module, it's not because you're a machine learning engineer that you should only be concerned with scale and running things and deploying things, in production and stuff like this. You should always make sure that you understand the problem that you're working with, and you should never be scared of go and do a little bit of model pipelining to see what kind of solution has been developed for your problem. And so here I'm just going to create a very quick pipeline, nothing too fancy, that basically evaluates very, very quickly 3 different types of models, some kind of bagging classifiers, some gradient boosting classifiers, and then some random forest classifiers. And I'm just going to see if I have consistently some good or bad results coming from each of these models. And because we know that some different kind of models like trees versus boosters and things like this generate usually quite different types of bias, right? Because they usually tend to overfit, underfit, and things like this. We're quickly going to get a feel for the type of bias that different type of model are going to give us, and it's going to be pretty useful to make at least the first choice of modeling that we want to do to solve this problem. And then obviously everything from this is iterative, and you want to improve on the solution and stuff like this. But for now, what we're going to do is we're going to create this pipeline, and for each model in this pipeline, we are going to generate some scoring. So we're going to train a very small model on this very small sample size of 10,000 rows. We're going to generate some predictions, and we're going to generate the accuracy, recall, and precision score for these predictions on the testing set, so that we have a very, very quick feel for what kind of model is probably going to generate what kind of results. And obviously this is far from perfect, but it's really great to have a first feel of what's going on in your problem. And so what we're going to do here is for each model, we're going to train basically the model, right? We're going to fit this model to the data. And so that's exactly why we're going to use this very conveniently named fit method of our classifier here. And we're going to train this model on the training data, right? This is the training data that keeps only the covariates, and this is the target variable that's basically used as label data to learn what's going on based on all of these previous hands that have been played before. And so once we have trained our model, we can do something like predicting on the testing set. And this prediction is going to generate precisely predictions so that we can compare them afterwards to the actual testing target variable. And that is exactly why once we have done some kind of predict proba, I don't know if there is an S or not, let's gamble. Once we have created a predict proba, we take these predictions, we basically say hey, when the prediction is above the threshold, above 0.5, say that we have won the game, and when it's below 0.5, say that we've lost the game. And that's going to be our predictions. And then we're going to compare that to the testing target, and we're going to get out of this the accuracy score. And this is actually just coming straight from sklearn. This is a pretty convenient utility that we can steal from sklearn metric. And once we've stealed it, we can do something like accuracy score, which is automatically going to tell us what is the score that we have. We're going to do the same with this recall score. And we're going to do the same with this precision score. And this here is exactly what we're going to be storing in our model evaluation class here, that is going to contain each of the models that we have in the pipeline, each of the names of the model that we have in the pipeline, each of the models themselves, and the metrics that we are going to generate for each of these models. And so that's why when you come here, basically, we're going to iterate on all of the models in our pipeline. So we're going to iterate on each of these guys one by one. We're going to do exactly what we've defined here before. We are going to generate the scoring. We're going to generate the scoring on this model, and we're going to pass all of the data sets that we need to be able to generate the scoring. It's the covariate training, testing, testing. So that's going to be allowing us to generate these metrics. And then we're going to keep this metric in this model evaluation class, which is going to be very convenient to access afterwards, like all of these things here. So what we're going to do is, once we have stored, let's say, this dictionary inside of our model evaluation, we're going to want to be able to access this metric by calling accuracy, recall, and precision, just as very simple accessors. When we call the property of evaluation as a convenience, what we're going to do is we're essentially going to go look up in this metrics dictionary, and we're going to see if we can retrieve exactly what we have stored, which is the accuracy scores. And so that's what we're going to get from here. And essentially, this is going to be very similar for everything. So same for the recall score, same for the precision score. We're going to go look into our evaluation. We're going to see if we can access the recall score. And behind the scene, what's going to happen is that we're going to call this self.metric. And so that is going to be pretty convenient, because once we have generated the metrics, now we can create these metric accumulators, which is just going to be a list. We're going to append to this accumulator each of the model evaluation that we create. And the model evaluation is just going to be like a class, like a holder, a container, whatever you want to call it, that contains name, models, and metrics. And now if we just want to print basically what's going on, we can just print the name of the model and the metric. But afterwards, it's going to be very useful, because we can do something like metric accumulator, get the first model evaluation that's contained inside of it. And because we have defined our model evaluation to have like a bunch of properties, now we can do like something dot accuracy score, and that's going to give us like the accuracy score of the first model. So that's going to be pretty useful. But for now, let's just run this stuff and see how it performs. It should take a bit of time, because we have 3 models that is going to run on data. So let's see. All right, so this should take a few minutes to run, and we can see quickly that our bagging classifier here has a pretty decent accuracy, pretty decent recall, and pretty decent precision scores, somewhere in the range between 0.76 and 0.78. And that's quite amazing. It means that without having done anything, just by having finished like the feature engineering and having cleaned our features in a decent way and having fed that to a very simple, non-optimized model, we can already get a model that is going to be very precise in some sense, very good at telling us whether we're going to win the game or not. So we definitely have hopes that our model is going to infer some pretty interesting patterns in the feature data, so that it can come up with this answer. The gradient boosting classifier, which is a little bit like, which has a pretty different, let's say, training approach to the way that it leverages the samples that it sees, is quite different in terms of like first impression, right? We have like a lower accuracy, lower recall, and lower precision score. It's quite interesting to see that it's performing worse, let's say, with this first impression than the bagging classifier. And again, like, I'm not really going to use that as a final decision, to choose one model or another, but it does provide like an interesting data points that tells me like, if I really have to take one development route and I have to start, with one modeling paradigm, then I might not want to go the gradient boosting route, let's say, when I see this. And then the random classifier here is somewhat closer to the gradient boosting. I do see like a better recall score out of the blue like this here with 0.75, but I see a pretty low precision score. Overall, it seems to be like the most nuanced. It's a pretty nuanced model, like as I can see it here. And I would be interested to just take the random forest route. Like, it seems like a good first model to start playing with. Let's see if we can come up with a decent solution before we go back and see if we want to revisit the algorithm that we use to train our data. So we're actually going to focus on this random forest classifier, but you guys do whatever you want. Like, I just want to go like that route here. And I'm going to take this random forest classifier. I'm actually going to instantiate it to run what is called the base model, or like the optimal model that has the optimal parameters. And this is not, let's say, the best practice in the world, because I'm not going to set aside like a validation set and a bunch of stuff like this to make sure that I train my hyperparameters on data that it has never seen and so on. So I'm not going to like be 100% best practice compliant here, but this is good enough to kick things off the ground. And let's keep in mind that we want to play with scalability today. We don't really want to become amazing data scientists. So I'm just going to do something like this. I'm going to create my random forest classifier, and I'm going to set up a hyperparameter grid that is going to check in a very dumb way, in some sense, what is the best parameters, what are the best hyperparameters for my model out of the one possibilities that I provide, right? I just tell him like, hey, just look for this hyperparameter list here and take the one that's best. If there had like some choice in there, then it would have been interesting. But just in the interest of time and speed, I just tell him like, you know what, just train this with these 4 parameters and let's see what you get out of this. And obviously at home, what you can do is you can increase like the search space so that you can see like, okay, what are some real parameter search that can happen here. But I'm just going to keep it like very simple for now so that we focus on scalability today. So I'm going to give it the hyperparameter grid. And then what I'm going to do here is I'm going to instantiate a randomized grid search that's going to allow us to find the best hyperparameters. So actually I'm going to use again a utility from sklearn here, and I'm going to launch this training with the base model. I'm going to give it the hyperparameter that we have defined here. Again, being very aware of the pointlessness of this hyperparameter grid here. And I'm just going to make sure that we run all of this stuff in parallel and we run a bit of cross-validation. And then I'm going to launch a random search.fit so that I can train this random search. And out of this random search, I want to extract the best parameters and the cross-validation results that we get out of this. And I'm going to launch these guys. And now we can head over to the terminal, right? Because now what we might want to do is make sure that our computer is working hard to tell us what are the best, like most optimal hyperparameter. And we can see here that, well, actually we cannot see a lot. We can just see that the hyperparameter grid has already run. It was so fast that I didn't even have time to check whether the workload was properly distributed across all of the cores of my computer and things like this. The reason why I was expecting that to happen, for the work to be distributed, is because we provide the parameter n jobs here. And we basically tell the sklearn utility like, hey, try to parallelize this learning as much as you can, just as many CPUs as you can, let's say, the host machine that you are running in. And for us, we actually have completed the run already. It was pretty quick. We could actually make it a bit more interesting and make it like 2 runs so that we see which one is working better. And so now we head to our terminal here, and we see that there is some pretty heavy processing that's happening in the background. We see that a few cores were being leveraged right now to do things. And well, again, we have run this, so now the job is completed. And we could come here, we could check like the cross-validation results that we had, and we can check the hyperparameters that we have gotten out of this. And our search tells us that these 10,000 estimators for the random forest, let's say like a better parameter to use for this specific, let's say, problem space. So pretty lucky to have decided to include it in the end. And so now that we have our hyperparameter, we can redefine it here, or we can use it directly like from this variable that contains the hyperparameter. And we can say, you know what, now that I have the best hyperparameter, train this optimal model on the whole training set, right? Because right now we have only trained on a subset of data, and we have only trained, using cross-validation. So now what we want to do is we want to retrain this model on the whole training set, and we want to see how do we perform on this new testing set that it has never seen before. And that is exactly what we're going to be doing here. We're going to take our random forest, and we're going to run this random forest, this newly instantiated random forest, because we have like a new base model. We don't want to use the previous one. And we're going to take this base model and we're going to pass it the hyperparameters that we have already found before, right? We're going to tell it like, you know what, make sure that you use these parameters that we have defined as the best parameters for this problem, at least, and on this specific data sample. Remember that this could be very different from what happens if we were to run more than 10,000 sample of data. And so now we're going to fit this stuff here. We're going to train on the whole thing. And if we want to save the model, we're going to like uncomment like these guys. We don't really need to have them like persist the model for now. So we're going to take this base model, we set the hyperparameters, and then we train this model on the covariate training and the target training. And we're going to see like what is our model going to perform, like how is our model performing. So we have a bit of training going on. It's quite fast, but again, we're running on 10,000 data samples and we're running 10,000 estimators, so it should be quite fast. And then once we have our trained model, we can generate the first predictions, right? So we use our optimal model, so the one that we just trained, to predict the probability on the test set. And we're going to keep these predictions, we're going to keep the target, and we're going to call this predicted value the prediction value, and binarize these to a 1 or a 0 based on the threshold that we have defined before. So we're going to run this. We're going to check our predictions. So we can see here we have the prediction, so we have the target, and we have the predicted. And now we can compare the target to the predicted to see how well we're performing. And that is exactly what we're going to do here. We're going to generate a precision and recall metrics. This is kind of like standard stuff. We're going to generate some precision recall curve and things like this. I'll let you guys go in more details into the code if you're interested, but essentially what I want to get to is this picture here that basically tells us, what is the first, let's say, a rock AUC that we have for this problem space, and what is the first accuracy that we have for this problem. And we looked at it, it's pretty weird and somewhat decent shape. We obviously trained the model on very few samples, so that's why it's so weird looking, and we can start looking at the model and what kind of features are important to predict like the winner of the game. And we can see that some features that we were expecting were going to be important are up there in top. Like we can see that the last bidder, whoever bids last, it is definitely like a big predictor in terms of like who is going to be winning the game. And we can see that the face value of the points, like how many points you start with, is pretty important as well. How many points your opponents start with is right up there, in the importance. And then kind of like the contract that you play is also pretty important. The number of jacks that you have is also pretty important. And remember, the number of jacks that you have is definitely like something that makes sense, in terms of importance, because when you have a jack in your hand, you just start with a lot of points, right? And so it should be there should be like multi-collinearity between how many jacks you have and how much points you have in your hands. But there are some interesting patterns that start to emerge. For instance, like how many jacks you have and how many nines you have. And this is not just important because if you have a lot of jacks and nines, you have a lot of points. If you have a lot of jack and nine in your hands, you're very likely to attack effectively the aces in the hand of your opponent. So in that scenario, there are like more signal than you would have if you only looked at the face value of the card that you have in your hand. So that's pretty interesting to think about. And now we've reached the point where, there's still a bunch more stuff that you can do. You can study the errors and stuff like this. I'll let you guys just play with the code, because if you want to become very good at solving this problem, then you're going to have to do things that I've done myself, which is really study in details this problem and really study in details the kind of errors that are being generated and come up, with ways to adjust the model so that it becomes better at learning when it makes mistakes. And I'm going to let you guys do that on your own time if you're interested. What I really want to drag your attention to is I want to drag your attention to the fact that we have trained this model on 10,000 samples. And this is far away from the, let's say, I think it was like 400,000 samples or more that we had. 400,000 samples that we have in total. So now we're going to go one step closer to running things at scale, in the sense that we're going to run exactly what we've done, but not with 10,000 samples row. We're going to do it with 100,000 samples row. And we're going to see what is the impact of doing that. So now we have 100,000 samples rows. And for instance, we're going to go back to our training of the model here, train the optimal model on the whole training set. And we're not going to touch the hyperparameter, just in the interest of time. We're just going to skip ahead to, just running things. So now, instead of running on 10,000 sample of data, what we want to do is run on the 100,000 sample of data. And so what we're going to do is we're going to recreate this covariate training, covariate testing. Now you can see that we have much more data. And once we have done this, we can go back to our model and we can relaunch a model here. And now we can see that it's still going pretty fast, but our computer is really reaching the limits of its core. Like it's really working very, very hard to generate this model for us. And obviously, like, it should become quite clear that, again, this is just running 100,000 lines of sample of data. This is not running on 1 million or 10 million or 1 billion samples. And so obviously, if we were to increase again, like, the workload, if we were to run, like, not the 100,000, but the 400,000, relaunch the same thing, we would see that we will quickly hit some limit in our computer's ability to train, let's say, a model fast, right? It's becoming prohibitively big in terms of data to be able to come up with a model in a fast way. And instead of waiting like 30 minutes for this model to train, what we want to do is to find a way to speed that up. And that is exactly the reason why we're going to move away from our local environment. I mean, my computer has been fighting bravely and he's doing everything he can to train this model. But at some point, it's time to move on. It's time to kind of like scale up. So I'm going to move away from my local environment, from my computer at all. Like, I'm going to stop running things in my computer. And I am going to refactor everything. And that is the file that you should have access to, especially I think the Udemy guys, like, this is the file that you should have access to in the Google Drive. I'm going to refactor the model development into a script, and we're going to see how we can move away from this in local environment here. So stick with me and get ready.